we are happy to have with us Audie Warren from the Radon Institute in Austria. I think of Audie as a promising young researcher in discrete geometry and additive combinatorics and their interactions. And I suspect this might be another topic that's on these topics. Today, Audie will talk about incidences in finite fields. So thank you.
Thank you very much. That's very kind of you. So yeah, thanks for the invitation. Letting me give a talk. You can all see the screen, right? This is all working, right? Okay, good. So yeah, so I'm going to talk about nonlinear incidence bounds in finite fields. So there will be two results in this talk. The first result is joint work with James Wheeler. And the second result is joint work with Ali Mohammadi and Tang Fan. So let's talk about some basics before we do anything. So what is incidence geometry? It's the study of the intersection properties of certain objects. So that's a very general thing to say, but in most cases where we try to apply these bounds to certain problems, we'll be interested in the case of, say, points and lines. So what does this mean? If we have a finite set of points P, for the moment I will look in the real numbers, we'll just keep it simple for the real numbers. And we have a finite set of lines L. We can define the number of incidences between P and L as this quantity, IPL. So this is the number of pairs, small p, small l, coming from P cross L, such that the point small p lies on the line small l. So really this is quite a simple quantity. All it tells you is the number of points which lie on lines from your two sets. Each constituent pair, small p and small l, is itself called an incidence. So this is why this is called, this quantity IPL is called the number of incidences. So yeah, in words, this counts the number of pairs of points and lines PL, where the point P lies on the line L. Okay. So the main question that we try to answer is, how large can this be? If we have a set of points P and a set of lines L, how large can this be in the worst case, let's say? So if we were to stick in the real numbers, there is actually an optimal upper bound here. This is called the Szemerédi Trotter theorem. And what it says is, for all finite pointed line sets P and L in R2, we have this upper bound. The differences between P and L is bounded by, so this less than sign here is the same as big O notation, just means that there's an absolute constant in front of the right-hand side, bounded by P to the 2/3, L to the 2/3, plus P plus L. So as I said, this is optimal. You can't improve any of the terms here. I see in chat, Adam has mentioned there's a new book about incidence geometry coming out next month. Oh, that's nice. I'll have to look at that. Talking about this bound here, we are really interested in this first term, the P to the 2/3, L to the 2/3. If we were to look in the balanced case where the size of the point and line sets are roughly the same, this is the bound, this is the term which dominates clearly. And these two extra terms, plus P plus L, are dealing with degenerate cases. So we can think of this P term as, or rather, let's look at the L term first. This really deals with degenerate configurations where you have, say, one point and all of your lines at one point. Here, well, the size of our point set is only 1, so our leading term doesn't give us enough incidences here. We really have L incidences here. One interesting thing, I suppose, is that the other error term, P, is dealing with the dual of this configuration. So there's a sort of duality here. And you can see this is reflected in the actual bound. It's symmetric because, of course, you can dualize the point and line sets, but this keeps the number of instances the same. and gives you this sort of configuration where you just have one line with all of your points on that one line. So this deals with very imbalanced point and line sets, but if we have a reasonable balancing, then it's this first term, which is the interesting one. Okay. So the Szemerédi-Trotter theorem itself is very widely applicable. It's got applications to number theory, discrete geometry. In most of the work that I do, we apply it to additive combinatorics. However, in some of the problems that we want to consider, points and lines aren't really enough. We want to think about other objects. So maybe a very classical problem would be the unit distance problem. And here we wouldn't want to look at lines. Here we'd want to look at circles, or unit circles. So it's interesting to change the object of line here to other things. In general, you could say we're changing lines to higher degree curves. If we stay in the real numbers, there are results known. There are quite a few results known like this, actually. I would say the most well-known one is the Pack-Sharir theorem. So here we can really give instance bounds between sets of points and some quite general set of curves. Okay, but the whole point of this talk is finite fields. So we now have a sort of landscape for the real numbers where we have an actual optimal bound for lines, and we can do things for higher degree curves. But what if we swap the real numbers for finite fields? Can we do things there? So it's rather obvious that the definitions of incidences swaps over very easily to finite fields. We can just define it in exactly the same way. However, a lot less is known. So lots of the methods of the proofs for the real numbers don't swap over to finite fields. For various reasons. You could say this is due to, well, we can't use topological information, we can't use the order properties. All these basic things that we'd like to do, we can't do in finite fields. Now, usually what this means is to prove things, we have to go to quite heavy combinatorial arguments, I would say, or character sums, things like this. But it's important that we can do some things. So one very widely used result in actually arbitrary fields, not just finite fields, is the point plane instance bound of Rudnev. So this swaps out 2 dimensions for 3, and it swaps out lines for planes. So what this states is, if we were to have capital pi be a finite set of planes in F3, where F is now an arbitrary field, and a finite set of points in F3, with at most k of our points being collinear. So we can't find a line with more than k points on it. If F has positive characteristic P, then we have to assume that our point set is relatively small. But if we have this, then we get an upper bound for the number of incidences between our set of points and our set of planes. So here again, we have this error term, k pi. This error term is very important because here we can actually be in the completely degenerate situation where we actually reach the trivial upper bound of p times pi incidences. So we can do this by having all of our points on one line and then have all of our planes containing that one line. However, with this restriction that we can only have at most k collinear points, we can deal with this degeneracy. So in that case, we get this upper bound. Now, what about this other restriction? We have this restriction saying if F has positive characteristic P, then the size of our point set can't be too big. This deals with another sort of degeneracy, which is when we were to take, say, all of the points in, if this were, for instance, Fp cubed, we could take all of the points in all of the planes, and we suddenly can't really say anything non-trivial. We know exactly what's going on here. So if we don't have these two things, if our sets are sufficiently small with respect to the characteristic, and we don't have degeneracies in terms of collinear points, then we can give an upper bound. Now, this theorem was used by Stevens U to generate a point line instance bound in finite fields. Again, this really should be arbitrary fields, but I will be focusing on FP. I should mention this. The reason that I focused on FP as opposed to arbitrary fields is because this restriction here depends on the characteristic. So really, if we were to look at some finite field, something like F2 to raise to a very large power, our restriction is so strong here that we can't really do anything. So we really want the characteristic to be big. So if we focus on just FP, we have this theorem of Stevens and Desiu. And what it says is if we have a set of points and lines in FP squared, and we have some restriction in terms of the sizes of the point and the line sets, then we get an upper bound for the incidences. And you can see this looks rather similar to the Szemerédi-Trotter theorem from before. So the Szemerédi-Trotter theorem had a exponent of p, or a leading term of p to the 2/3, L to the 2/3. Here we've got something weaker. We have an extra 1/15 in each of these. But we have the same error terms for the same reason, really. But it's important to realize that this is a weaker bound. Okay, so in order to state the new results, I want to give some contextual trivial upper bounds. So it's completely and utterly trivial to say that the instances between P and L is upper bounded by the size of P times the size of L. But we could do something quite a bit better than this, just using some basic geometry. So, yeah, completely trivial upper bound would be PC. But if we were to just use the simple fact that two lines intersect in a point and 2 points define a line, we can get something quite a bit better by using the Kavary-Shoshtouran theorem from graph theory. So this fact actually implies that in what's called the incidence graph, we don't have any copies of K22. There's no K22 in the graph. And this tells us that, in fact, the incidences can be bounded by the minimum of P times root L plus L, and then L root P plus P. So importantly here, in whichever one of these happens to be better, one of the two factors, P or L, comes to an exponent of 1. Okay, so either we have P L to the 1/2 or L P to the 1/2. So these are the sort of contextual trivial bounds that we want to beat. And the theorem of Stevens and Desiu does beat this in a certain range. So if we have a certain balancing between L and P, it's written down here, L has to be bigger than P to the 7/8 and less than P to the 8/7, then it's better than this trivial upper bound that we get just from very basic geometry in the Kavary-Shoshtouran theorem. Okay. So we do have this non-trivial bound for lines, i.e. it's non-trivial, meaning it's better than this minimum here in some non-trivial range. But can we do anything for other types of curves? So what previous non-linear results do we have? When I say non-linear, I just mean an instance bound for objects other than lines. So there were some non-linear instance bounds known before. The first one, to my knowledge, was due to Bourgain, who gave a qualitative bound between Cartesian product point sets A cross A and sets of Möbius transformations. So I say qualitative because it just beats the trivial bound from the previous page by some nondescript epsilon. Shkredov gave a stronger bound for Cartesian products which are not balanced anymore, not symmetric anymore, A cross B, and curves which are actually translates of the hyperbola xy equals 1. Okay. And again here, this has to be a very specific set of points, i.e. it's a Cartesian product A cross B, It's also a very specific set of curves because the curves have to themselves be defined by a Cartesian product C cross D. So this is a very structured result. The most recent result was due to Rudnev and Wheeler, who gave a quantitative result which beats Skredov's result for Cartesian products A cross A and again sets of Möbius transformations. Now, something which you might notice from these is all three of these results actually do pertain to Möbius transformations. So the first one and the last one explicitly, but the middle one, this is a sort of smaller set. This is contained within the Möbius transformations, but they're certainly Möbius transformations themselves. And this is interesting because it means that the three non-linear results that we have are all talking about the same family of curves, i.e. possibly subsets of the Möbius transformations. This was interesting because it's, you kind of ask, well, why is that? So let's have a brief recap on what Möbius transformations are. So for this talk, we're going to only talk about Möbius transformations over the finite field FP. It's a bijective function going from the projective space over FP to the projective space over FP, defined by this projective equality. Now, this is actually rather important for us, that we think about these things projectively as opposed to just the standard definition. But if we were to take this definition here, this f of the projective point xy is this linear combination here, and restrict it only to the affine part, then we just get the normal definition. Okay, so this definition down here would be the standard definition, which I'm sure most people have seen. Now, something very important is I will very often swap between the notion of a Möbius transformation as a function, i.e. f of x going from the projective space to the projective space. And I will sort of conflate that with the curve in FP2 given by y equals f of x. So sometimes I might mean one of them, sometimes I might mean the other one.
Can I ask something? I'm not so sure everyone are used to this curve. How does it look like exactly? What should we use?
So these look like hyperbolas. So they have, well, I will explain this later, but okay, yeah, maybe I should explain this more. But these look like morally they look like hyperbolas. They have one vertical asymptote, one horizontal asymptote, which we'll see later on. But they don't always look like hyperbolas. If you were to set C to be 0, then suddenly they're lines, which is another important thing that we'll use later. So you should think of these either as lines or as things which look like hyperbolas.
Thank you.
No problem. Okay, so yeah, so I'll explain this later, and I'll give whatever things that we have to use whenever we use them. But we really only use basic facts about these things. Okay. So let's do some context again. So I talked about the trivial bounds for lines before. What trivial bounds can we say for these Möbius transformations? I should say that these are conical curves. Y equals f of x. These are conics, certainly. And what this means is if we take two Möbius transformations in FP2, they can only intersect in at most two places over the affine plane. So what this means is if we use the Kavaria-Schoch-Turan theorem again, the instance graph now contains no copy of K23. And so we get the upper bound, the trivial upper bound of p to the 1/2 t plus p, and pt to the 2/3 plus t. So, okay, the numerology here maybe isn't too clear or important. The only important thing really is, again, in whichever one of these happens to actually be the better, the leading term always has a factor with exponent 1. So either a t to the 1 or a p to the 1. It's also not symmetric. We have a p to the 1/2 t here, but over here we have a pt to the 2/3. Now, if we were to do the same thing for conics in general, So Möbius transformations are a subfamily of the conics. If we were to do this for conics in general, we would change out our 2/3 here for a 4/5. Okay. But again, we still have this thing of, okay, P here appears with an exponent of 1 and a C here appears with an exponent of 1. So the important thing, and why I've said that multiple times now, is if we were to prove an upper bound which had both of these factors to an exponent less than 1, then we know that there's some non-trivial range where this bound that we've just given is better than this minimum. Okay. Okay, main results. Then I'll actually swap over to a whiteboard, and we'll do the rest of the talk there. So the first result, really the important thing here, by the way, is not the numerology. So there's lots of numbers here, and it's not so important that you understand what they are really. But the first one says, let T be any set of Möbius transformations and P a set of points in FP2. We again have this restriction that our point set can't be too big, so that we can't take some degenerate thing where we take all of our points and all of our transformations. If we have this, then we get an upper bound which has P and T both to an exponent less than 1. It's actually P to the 15/19, T to the 15/19. So this leading term, again, is the important term, and it's better than the trivial Kavary-Shostaran bound in a non-trivial range. So this is better than this minimum that I showed you on the previous slide. The error terms here are less important. I guess all I could really say is the T is exactly the same as it was in the Szemerédi Trotter theorem, for instance. It's just an error term of T. But the other error term is sort of bigger than it should be. And this is an artifact of the method that we use. But really, these second two terms aren't important. It's this first term which we really care about. Then we have a second theorem. So this second theorem is the joint work with Ali Mohammadi and Tang Pham. And this exchanges Möbius transformations for conics in general. So if we take any set C of conics in FP2 and any set of points P, again, we have the same restriction, our point set can't be too big. Then we have a non-trivial upper bound for the number of incidences. So again, here we have two exponents which are less than 1, which gives us a non-trivial range of balancing where this is better than what we knew before. And we have a first error term which is bigger than it should be because of the method. And then a second error term which is basically the same as the error term from Szemerédi Trotter. Okay. So to summarize this slide in a nutshell is we have non-trivial bounds for Möbius transformations and we have non-trivial bounds for conics. Okay, so I'm going to swap over now to my whiteboard. Here we are. And I don't want to give any technical details at all or anything like that. I'm just going to give the idea of the proof, which I think is very simple. So what do we have? We have a set of these Möbius transformations. Let's call it T. And we're going to have to use one previous result. It was this result which I put on the screen, which is a line instance result in FP due to Stevens and Desiu. So Stevens and Desiu, they have an instance result for points and lines. And if you were to rephrase this, this is actually an upper bound for the number of K-rich lines, which I will explain in a second. So what does this mean? Well, if we have a line in the plane and we have a set of points, our line is called k-rich if it contains at least k of the points from our point set. So here, this line will be 3-rich. It has 3 points on it. It's also 2-rich and 1-rich, importantly. So we're not saying exactly k, we're just saying at least k. And so this incidence result for points and lines can actually be rephrased in terms of an upper bound for the number of k-rich lines defined by a point set. That is, given a point set P in FP2, how many k-rich lines does it define? Okay, so this is something which happens with the Szemerédi-Trotter theorem and in general with instance bounds. You can usually swap them between a sort of standard way of writing them as an incidence result and writing them as an upper bound for k-rich lines. Okay, I hope that's okay. And we understand that we now have an upper bound for k-rich lines. I won't write down what it is. It's not important really what it is. We just know that we have it and we can deal with this. Okay, so armed with that one result, let's give a sketch of the proof. I'll make sure that I have the chat open so that in case I have any questions. So the proof, again, like I said before, the main idea going into it is very simple. So let me draw a picture here. Here we have a set T of Möbius transformations. Like I said before, they look like hyperbole. Now, how are we going to deal with this? We want to give an incidence bound between our set, our blue set of transforms, and let's say we have this red set of points. Well, what we're going to do is actually give a bound via each individual point. So we look at this sort of locally. So let's fix some point Q in our point set. And let's say it's actually this one here. Okay. Now Q can be given a label. Let's call it the pair Q1, Q2. And we will restrict our set of transformations now only to those transforms which go through this one point. If we're looking at incidences and we have fixed our point Q, we're no longer interested in any of these transforms which don't go through our point. They don't matter at all now. We're only going to look at, let's define it as TQ to be the set of transforms from T which pass Q. Okay. Now what we're going to do is bound the number of k-rich transforms in TQ. Okay. So what basic facts do we know about these things? Well, if we were to take some transform which is in TQ, by definition, we know one thing about it. We know that f of Q1 equals Q2. This has to happen. If this didn't happen, it wouldn't go through the point. So we know that it sends Q1 to Q2. Now we need two other things. And they're both very simple, really very simple. The first one is that lines are Möbius transforms which fix the point at infinity. I'll explain what this means. And the second one is the composition, or maybe I'll state this as an even simpler statement. The Möbius transforms form a group. Under composition. Okay, so let's explain these two things. The first one, what do I mean when I say lines are Möbius transformations which fix the point at infinity? So to illustrate this, let's write down a Möbius transform in general. F of x is ax plus b over cx plus d. Now, I said before that we would really like to use this projective definition because it will illustrate what's going on better. But what we'll really notice here is this certainly has an asymptote, vertical asymptote, if and only if c is not 0. Okay. So what happens if c is 0? If c is 0, then this thing on the bottom here disappears. We end up with a line. And if we were to then go back to our original projective definition, we would see that f of the point at infinity 1, 0 is actually equal to 1, 0. It's impossible for it to be anything else because a line maps points of fp to other points of fp. It doesn't send you to the point at infinity ever. So this first thing is simply saying that they fix the point at infinity. The second point, Möbius transforms form a group under composition. This is easy. This is very well known. If you were to take two Möbius transformations, f and g, compose them together, you would get another Möbius transformation. Okay. I hope everyone is okay with that. So the next step is to draw a sort of, we're going to take our set TQ. These were the transformations which passed the point Q. And these really are transformations, i.e. they're not lines. Well, what we're going to do is pre and post compose with some specially chosen transformations. And then once we've done this, the resulting set will actually just contain lines because we will have chosen our pre and post composition elements in such a way that this happens. So let's explain this a bit more. Again, what we know is, I'll draw a box around it up here. We know that for all of our transformations f in TQ, f of Q1 is equal to Q2. So let's pick two other Möbius transformations. Let's call them G1 and G2. Now they're only picked with one restriction in mind. G1 has to send the point at infinity, 1, 0, to Q1. This is only one restriction. So actually we have a whole load of different choices for what we choose as G1. G2 is going to take the point Q2. Oh, sorry, I shouldn't really say point here because now we're really talking about an element of FP. It's going to take this element of FP Q2 and it's going to send it to the point at infinity. Just a single restriction for each of these transforms. Okay, now the composition, if I were to write this down in hopefully an understandable way, in the middle here, what we're going to do is have an application of f. So if we think of this as our function, with our f sends q1 over to q2. Now, if we, right at the beginning, before we even apply f, we were to apply, now which way around do I want this? I want this to be g1. And on the right-hand side here, we're going to apply something on the end again. This is going to be g2. And what do we see? Well, if we were to chain these together, so we're now looking really at the composition of doing g1, then doing f, and then doing g2. What happens to the point at infinity with this composition? Well, first off, by definition of g1, the point at infinity gets sent to q1. Then we have to apply f, which we know sends q1 to q2. Then we can apply g2, which is going to send q2 back to the point at infinity. Okay? So the only important thing here now is this composition. Now, I always get this the wrong way around. How do I want to do this? This should be g1 first, and then f, and then g2, right? This composition here is a Möbius transform, because this is a composition of Möbius transforms, and the Möbius transforms form a group. And it also fixes the point at infinity, which is what we've just shown, right? So we've got a Möbius transform which fixes the point at infinity. What does this mean? That means it's a line. So this is the important thing here. This composition is a line. Okay, so now we look at the entire set. So F here could have been anything. So we now look at the entire set, G2, TQ, G1. And this set here is actually a set of lines. Okay. Now, there are some technical details which I don't want to give at all, but suffice it to say, when we do this composition, we only lose one incidence. That one incidence actually corresponds to the point Q. And what we get is a transformed set of points together with a set of lines, which are K-rich. And then we can use this previous bound up here of Stephenson's U, which then can upper bound your K-rich lines. What this means is applying Stephenson's U to this set, this composition set here, is now valid and lets you give an upper bound for the number of K-rich transforms going through Q. Now that is actually the entire heart of the proof. Everything else is just standard stuff, which has been known for, or is standard practice in instance geometry. So we have to do things like dyadic decomposition. We have to refine things at the start. I guess the only other non-standard thing is this is only a local bound for one Q, one point in our set. And so we end up having to actually sum over each of these points. Now, summing over each of these points does seem like a weakness to me. So if this argument can be improved, then that would be my first place to look. But that's what we have to do, right? We have to sort of bound the K-rich transforms in the entire set by looking locally. So if I just write down here, plus some known technical stuff. Implies that we are actually done. So this gives you the first theorem, the theorem with James Wheeler on instance bounds with Möbius transformations. Okay. So for the second bound, I would say it's almost simpler than this. The second bound, the one for conics in general, so arbitrary conics in the plane, I would say that it's almost a corollary of this, and you can prove it almost immediately. So why do I say this? Conic bound. So for this, we're not going to have a set of Möbius transforms. We're going to have any set of conics. So we could have circles, we could have parabolas, we could have ellipses, we can have whatever we wanted. And let's call this set a capital C. So conics is a set of, C is a set of conics in FP2. Here, we will actually only use one fact, and again, it's very simple. You can prove it really easily. I'll write it down here as, I suppose, a lemma. If gamma is an irreducible conic in FP2, then gamma is a Möbius transformation if and only if. Now, what do we know about these Möbius transformations? So what I said before was they would either be a line, or they would have a vertical and a horizontal asymptote. So if I write down the equation again, y equals ax plus b over cx plus d. Well, in this lemma here, we're looking at irreducible conics. So we're not interested in lines. So we can assume that c is not 0. Now, all of these things, by saying that they have a vertical and a horizontal asymptote, what I really mean is that the curve contains 2 specific points on the line at infinity. In particular, 0, 1, 0. So which one's this? Okay, so this would be the vertical point at infinity, and this would be the horizontal point at infinity. If this set is contained in our irreducible conic, then the conic has to be a Möbius transformation. Okay. So again, this isn't anything, I hope this isn't anything mysterious. This can really be proved simply just by writing down the equation and assuming that these 2 points lie on the conic. Okay. Now, the process is similar to what it was before, but simpler, I would say. So if I draw another picture here we have a set of conics in general. So we might have some hyperbolas, we might have some circles or ellipses, we might have some parabolas, whatever we happen to have. And we also have a set of points. And again, we're looking at the incidences here. Now, before we fixed one point and we called it Q, and this one point was sort of vital for the analysis that we did. Here, we have to do something slightly stronger than that. We have to pick 2 points. So let's say, I don't know, we pick 2 points. I want to pick these in a specific way. Let's pick this one and this one. Let's call them Q1 and Q2. No, let's not. Well, these things already have names. Let's call this Q and Q prime. Okay. So we just fixed these 2 points. And now, like before, if you remember before, we defined this set TQ, which were the transforms which went through the point Q. Well, here we're going to do something similar. We're going to define the set C, Q, Q prime. So these are now going to be the conics that go through both of these points, right? set of conics from our set, which go through both Q and Q prime. We're almost done now. All we're going to do is take any projective transformation which sends the point, let's call it pi, any projective transformation pi, such that pi applied to Q is one of these points at infinity, and pi applied to Q prime is the other point at infinity. So it's going to send Q to, what is this, the vertical point at infinity. It's going to send Q prime to the horizontal point at infinity. Now, the question that we ask ourselves is, what is pi of gamma for gamma in CQQ prime? So, one basic thing, whenever we apply a projective transformation to an irreducible degree D curve, it remains a degree D curve. So after this transformation pi, these irreducible conics have remained irreducible conics. Secondly, because the conics had to contain the point Q and Q prime, after this transformation, this new conic, pi of gamma, has to contain the vertical point at infinity and the horizontal point at infinity. In particular, we can use this lemma up here, because now we know that these 2 points lie on, well, on the right-hand side here, it would be pi of gamma. But this is then saying that pi of gamma is a Möbius transformation, okay? So let me write this down. Both of these points lie on pi of gamma, which implies pi of gamma is a Möbius transformation. But this applies to any of the curves gamma. So this actually means that pi of CQQ prime is a set of Möbius transformations. And we're now at the stage that we were at in the previous proof, where I say, okay, now from here we can do everything in a standard way. So it's now technical, and I don't want to get into it again. But this is sort of iterative, where now we have reduced our set of conics, or a certain subset of our set of conics, to a set of Möbius transformations. We can then use the incidence bound that we just gave, i.e. the one for Möbius transformations, to bound the incidences. We again have this idea of, we've only this sort of local bound for the conics which go through two of our points. And so again, we have to sum over every pair of points in our point set. And like I said before, this seems to be perhaps a weakness in the argument that could be improved, or at least that would be the first place that I would look. But again, the heart of the argument is this, where we reduce our conics to transformations sort of locally. And you'll see it's really the same thought as with the other proof. You take a more complicated object and you sort of you impose more restrictions on it. So here we're imposing that it goes through 2 points, or up here for the transformations, we impose that they go through 1 point. And that imposition reduces the, and we can then actually map this smaller family to a set of objects that we can already deal with. So here the transformations become lines because we've reduced the dimension by 1. Here we've taken conics which have dimension 5, i.e. they have dimension 5, and when we impose 2 restrictions on them, they come down in dimension by 2 to 3, which suddenly matches with Möbius transformations. So this main idea of, I don't know what I would call it, maybe degree reduction or something like this, by fixing things, is the heart of the proof. Everything else is sort of technical stuff that we've already known before. Okay, and then just to finish, I guess I would mention perhaps future problems or future research. The natural thing to do here, I think, would be to start looking at degree 3 curves, but suddenly things start to get more complicated and it's not clear at all what you're supposed to do. For conics, it certainly works because, like I said, conics are degree 5. You can fix 2 points. When I say conics are degree 5, what I really mean is a conic is defined by 5 points in the plane in general. So sorry for my loose definition there, but when we go up to degree 3, suddenly we need 9 points to define a curve. And so if we were to think, okay, we're going to reduce these to conics, we would suddenly have to fix 4 points in the plane and send them to something. However, we can't really do this because projective transformations act 3 transitively. We can only really think about 3 points maximum. So it's not clear what we can do with cubic curves at the moment, unless there's some sort of subfamily which is bigger than conics but less than cubics, which gives us this sort of stepping stone between the two, which I think would be nice. But that would be my next stage in this research. I should also say that the papers that I mentioned, the 2 papers where these results appear, have various applications of these. So we give applications to some product problems and combinatorial problems. So these certainly do have at least some applications. Okay, I think that's all I wanted to say.